Hi guys, I hope you had a good chat during the break with the other version of me or myself. Thanks for your patience for the ones who survived the first part. Let's start talking about the CRL itself. I think is the most exciting part of the tutorial. Um, the the idea is like CRL challenges and learning opportunities. The idea will try to list some of the representative tasks that I envision for CRL, which I feel are kind of quite general new learning opportunities. Also, each one of these tasks has a new component that is present, I believe, is present in the real world and hasn't been studied before. And I think this makes them appealing. We use the language of causal inference, of causality, and the PCH, the CHT, and in other words, the model of the environment M as CMM and the graph G to try to start understanding and then solving this task. There are six tasks or six dimensions. The first three, I'll try to spend the strategy here or the organization, the outline is like I spend around 15 to 20 minutes in each of these three to give the idea of the task and some idea of the solution, possible solutions. And then I'll kind of make a brief summary, 1 minute or 2 minutes of the other three tasks, given that there is no time of talking about all of them. The task one is what we call generalized policy learning. So far, we assumed that the word was kind of cookie cutter in the sense that they exactly match these two modalities: the online learning and the offline, meaning three. The offline, that is the off policy, and the do calculus or causal calculus kind of learning, that can be the soft do, and modes of learning. Then we'll see in maybe 2 or 3 minutes that the first example where things don't work very well, they get more involved, and these methods alone cannot solve the problem. Then this is what we're calling GPL, or generalized policy learning. Then I'll move to the second task, that is when and where to intervene. We also assume throughout the literature that interventions are always good. If you can't change something, I should just do it. I should just change. I should just go to the system and make the intervention. Here we will consider whether the best thing to do may be just to allow the system to evolve naturally without touching it. Perhaps sometimes when you touch, you kind of mess up with things. We like to understand these conditions. On the other hand, if the interventions are necessary, we'll consider where to intervene in the system. Where is exactly can you be surgical and just change what we need? Here has this idea of refining the policy space that I would like to discuss. Everyone talks about policy. I'd like to talk about the policy space and a little bit more about how I feel it, or what do we feel about it, I should say. Task three, throughout the literature, it's assumed that the agent has some type of automata-like behavior and do not do introspection, do not do counterfactuals. Here we consider endowing the agent with capability of doing counterfactual reasoning in a relatively general way, layer three, which will lead to a different type of optimization function that is conceptually different, but we'll try to make as close as possible to the task that we understand that is in layer one, layer two.
So you're tuning in. Sorry, I'm starting a bit late today. Continuing with this causal reinforcement learning ICML tutorial from the 2020 ICML, and so these are the three tasks that Elias is trying to apply causal reasoning to within the reinforcement learning space. And what's interesting is that task one and task two are clearly tasks where you could save some resources, right? Like train with less data. If actions eat up some kind of resource, then to be more conservative with your actions. Task three, however, and to me is very interesting because it's pushing the frontier of what reinforcement learning or more generally agent modeling can do, right? We're talking about intentionality, free will, autonomy, as opposed to agents kind of behaving like pre-programmed automata, and so this is, and so those are philosophical concepts, but of course, if you can kind of formalize them, then in theory you can get an agent to do things that the current state of the art would have trouble doing. So especially with counterfactuals, because whenever you see the word counterfactual, you can always kind of reason like, oh, okay, well this is learning from data that I'm imagining as opposed to data that or learning from a world that I'm imagining as opposed to a world that I've seen. And so this means that you could train an agent on in other words, that if an agent's limited to the training data, then it cannot do things that are beyond the scope of that training data. But if it can imagine scenarios that it hasn't actually observed in training data, then it could it could do something with those imagined scenarios. And so this could expand the frontier a little bit. So that tends to be where my interests lie.
Then the problems that I talked last about, the first one is called generalizability and robustness across environments. I just mentioned this problem that I worked for many years called the transportability. The idea here is like, suppose that you allow a robot or a system to interact in a particular environment, perform experiments and so on, like in the California desert, that we have a rover that is able to dig rocks and understand how to operate there. And now we send the rover to other place, to other environment, like Mars, and you like the agent to operate efficiently, avoiding to do too much experimentation, given if it breaks, things are pretty bad, given that it's far from here. And the question is like, what are the anchors that allows one to extrapolate across these different settings or across these different environments? They are for sure causal. As you know, there is structural invariances that we discuss about the modularity, and we like to understand this a little bit more in the problem of transportability. Main topic of my PhD thesis that here is present in reinforcement learning in a substantive way. Then the task number 5 is learning causal models by combining observations and experiments, L1 or L2 data. So far, we assume that we're operating over a specific model of the environment. Can be these kind of templates, as I mentioned, can be a multi-arm bandits or MDPs or POMDPs, or it can be crafted by hand, instrumental variable, the front door, or so on. In reality, we would like to operate somewhat in between and don't commit so much the structure. We like to be flexible, and especially in reinforcement learning, that the agent already have the capability to do interventions, then it should try to leverage that and combine the observations and interventions in order to build its own causal model. I think it's very natural if you're considering to grow a baby Einstein as a baby AI, and the baby AI should be evolving its causal model or equivalence class of causal models. There are some subtleties there, but there are some kind of very exciting new results here. Huge literature that is in structural learning that was just learning about the how to learn from observations. This recent piece of work is saying, oh, world is much bigger. And whenever in RL, we're already doing the interventions, then let's try to leverage that. We already have layer 2 capabilities. Third task is about causal imitation learning. Babies as well learn by mimicking other humans or other babies. So this is kind of well known, and this motivation to imitation learning literature. I think the nice observation here in the causal arena that the learner and the demonstrator can have different causal models. And it turns out that imitation is not necessarily what we want, or at least there are limits about when you should just be imitating other agent, and even when the other agent is an expert. Then the question here, we like to try to understand under what conditions imitation is safe, and given that you don't observe the Y variable of the expert. I think it's quite unique. There's some kind of quite unique insights from the causal folks, from the causal side, and the task is quite cool. But now let's get into it. Let's start talking about the tasks.
Go back a second to these stories. So this is, generalization, robustness. So this, I think, is extremely important because this is the problem, right? We train bots in virtual environments, and then we put them in actual robot bodies, and they seem to fail pretty poorly. And so this generalizability and robustness, transportability, structural invariances, that's, I think, also going to be quite crucial for getting reinforcement learning to work. And so learning a causal model. So I mean, oftentimes we might believe that the agent starts with a model, but why not have the model improve? Why not have the agent improve their model over time? And then finally, this causal imitation learning. So imitation learning is when agents learn from other agents. And I'm really curious about this because when you're learning from another agent and you observe them act according to a policy, do you assume that agent is some kind of, like he said, passive automata just reacting to stimulus? Or do you, and therefore like treat that act as a random variable? Or do you treat the other agent as some active thinking, deliberate agent that is using and is choosing its actions based, and so you model that using intervention? I'm very curious about task 6.
and it turns out that imitation is not necessarily what we want, or at least there are limits about when you should just be imitating other agent, and even when the other agent is an expert. Then the question here, we like to try to understand under what conditions imitation is safe, and given that you don't observe the who or the y variable of the expert. I think it's quite unique. There are some kind of quite unique insights from the causal folks from the causal side, and the task is quite cool. But now let's get into it. Let's start talking about the tasks. I would like to talk about this generalized policy learning. This is work with my PhD study, Justin Zhang. Online learning is usually undesirable due to financial, technical, or ethical constraints, as we already discussed. In general, one wants to leverage data collected under different conditions to speed up learning without having to learn from scratch. On the other hand, the conditions required by offline learning are not always satisfied in many practical real-world settings. In this task, we want to move, or we move, let me be positive here, we move towards realistic learning scenarios where these modalities come together, online and offline, including when the most traditional and provably necessary assumptions do not hold. That's important. This is necessary and provably necessary. Let's start with an example. Suppose consider this setting that we are trying to learn the input. We have an input distribution that is P of X and Y. X is the action, Y is the outcome or decision, Y is the outcome of the reward. And we would like to learn a P of Y given to X, P of prime, Y given to X. This could be in robotics that we're trying to learn by demonstration when the teacher can observe a richer context than the student. For example, has more accurate sensors. Maybe an expert, a baby robot is trying to learn with the older robot, and the older may be having infrared, but the baby didn't develop this skill yet. Or in the context of the medical optimal experimental design from observational data. Let's take for the example, given that we already used some medical example here. As input that is coming from this data set P of X and Y, you have X that is the decision, Y is the outcome, and you have this exogenous set of unobserved variables that is both affecting the X and is also affecting the Y. This is coming from physician of a collection of physicians that is coming from for example, Columbia Hospital. You have, 1 million data points there. A small number, by the way, you have much more. You have 1 million data.
I'm turning off the mic because my wife is putting together some IKEA furniture in the background. But anyway, I'm not really clear here if we know what the DAG is or not, right? Like, do we just know we're doing an action, we're getting some outcome, and we know there's some confounding, but do we have any structural idea of this confounding, or we just assume that there's confounding and we're just trying to go from here, and we're trying to learn this from this without actually knowing? Because if you know what the DAG is, right, then this is easy, right? You just kind of, well, maybe it's harder, but it's not. I guess it's not any easier. There's knowing the DAG if you don't observe you. Oh, that's interesting. Okay, so let's see where he goes with this. So I guess DAG or no. If you is unobserved, then you're out of luck. And not unless the do calculus gives you some kind of identifiability, which I've proven. I'm not sure what he's going to do.
Points P of X and Y. Now the task is try to learn what is the causal effect of the drug in the outcome. And for example, the FDA or anyone that wants to understand causality seriously will say, oh, what I want is the P of Y to X or P of prime Y to X. I'll stick the pi just implicitly. That is the one that is picking the value of X. We'll actually learn the P of Y given to X. And in some way, we like to, which means that is the graph, that there is a pi here pointing to X. This is the P of Y given to X. And yeah, that's the task. That's the task. Now, what we just spent 1 hour here. Hopefully, it was okay for you guys, or not suffer a lot of suffering. But I try to categorize, and then one of the modalities that I claim to have in the literature is the off-policy learning. It's one of the 2 offline methods that we have. The off-policy learning. If you try to apply in this setting, we have a violation of the A2 assumption. If you don't recall, you go back. But A2 means here that A1 is okay. A1 means that you are controlling the same variable. Here we are trying to get the effect of X. X is the action. And here, or you have X as the action. That is what the physicians decide. And here we are trying to control X, the effect of X as well. Then A1 check. But A2 is the assumption that they are observing the world in the same way. They have the same context C. That while here it is not the case. This doesn't hold. The physician can observe a richer context. Maybe the physician didn't take note in the EHR, the health record, or maybe can be in the subconscious level as well. I'll not get too much into that, maybe in task 3, but maybe the physician is just affected by the way that the person is looking, or what the prior beliefs that they have about this type of people that affects X and Y, whatever type is that. Then it's very common. The FDA comes in, or any serious policymaker or decision maker will say, man, there is confounding data, there is confounding bias in this data, I cannot use it. I need to conduct an experiment. Then whatever, this is the justification, formal justification for that in terms of the off policy here. If you try to do the second off policy offline method, that is the do calculus, believe me, at least for now, we can check later, but also do calculus or the soft do calculus, sigma calculus by Juan Correa, you say not possible to do the inference in this case. Then it seems to be justify this feeling that we need to go online. What else? Now, my suggestion here, given that we have these 1 million data points, and online is a small number here of experiments that we do, maybe with 300 people, and we spend, I don't know, maybe $5 million, I would suggest the following. Let's ignore that the physician and the FDA, quote-unquote physician, quote-unquote FDA, these two agents. Let's ignore their differences, and let's pretend that the physician and the FDA are exchangeable.
So one thing I didn't capture here was this A2 assumption here. I think he was saying that it's something about they see the same model, but perhaps they have different granularity. I'm actually should I play that again? Learn by demonstration when a teacher can observe a richer context, more accurate sensors. So yeah, this distinction here, not really sure what that means. What does it mean that the teacher and the learner can have different contexts? Isn't context something would reflect on a DAG? I'm not sure. Let's ignore their differences and pretend that the physician and FDA are exchangeable, called naive TS. In other words, naive TS attempts to use observable data as prior. All right, I don't know. We'll see. I guess if it kind of feels like we're figuring out what we can actually do and then working backwards from the solution to kind of pick a problem, but I guess nothing's wrong with that if it's a useful problem.
It can be technical, but at least for now here, let's use informally. That means that they're the same, qualitatively the same causally, and let's call this the naive TS, not a leading title, but a name, but naive TS. Now, in other words, the naive TS will attempt to use the observational data as a prior. You'll get this P of Y given X here, and we'll try to seed or to use it as a prior in some way to allocation procedure. You do that. By the way, I should mention, I'm using TS Thompson sampling. You can pick whatever method you want. My goal is just to get the simplest possible setting that I can disentangle the issue that I want to talk about. You can put UCB, you can put with NDPs, whatever method they are, and so on. Any method that is doing allocation, that's fine. This will happen as well. What's the smallest one? I'll get TS, that is the easy one, to talk at least here, and this flavor of the prior comes up naturally, and I'll get binary variables. That is the most constrained setting. If you have any type of discrete or any type of continuous, there's so many degrees of freedom. You'll see in maybe 4 or 5 slides that will be even more likely that this problem is happening, or obvious that will be happening, I should say, because here it will happen all the time as well. Okay, now, but the plot doesn't look very good. For sure, we should show more. Perhaps there is some kind of nice behavior there, but so far, picture is not good. This is the number of trials, this is the cumulative regret. Note here that the oracle who is validating that is the environment SCM that I show in 1 second. Now, okay, but at least we have some kind of indication some kind of that picture is not going, it's looking too like straight, it's like a flat or kind of linear. Let's call this traditional TS, means ignoring the observational data. This is what we have when you throw away all this data. And this behavior that is kind of the expected one whenever you teach, I don't know, basic AI or undergrad AI, this is what we got. Textbook kind of setting. Now, the obvious questions here, what you should be asking, or what I'm asking when I first found that, is like, how could this be happening? It seems to go against all I understand when I put my statistical hat here, my statistician hat or machine learning hat. It's like, man, one of the basic axioms here is like more data is always good. Now, apparently, the data is hurting. If I had there, I'll be pulling the hair here.
See, it would be interesting if somebody, I've said it before, like a really low-hanging fruit, I think, would be to actually go and take these ideas and implement them in OpenAI Gym and show, like, because these kinds of FDA physician questions, I mean, that's not what people train reinforcement learning algorithms on, right? They train them on bots acting in virtual and real environments. If you can get proof of concept first. So whatever he's talking about here, I'm not really understanding the setup of the question, but he's showing that he's constructed a problem such that using data is better than, or starting off with like a history of log data is better than not. Sorry, starting off of log data is worse than not starting off, and I'm sure he'll show some kind of adjustment to show incorporation of causal ideas that fixes the problem. But again, I struggle with these 3-node examples because they're just not particularly convincing, in my opinion.
But I with my hat. Then there's this kind of uncomfortable situation apparently. I would like to try to open up this plot here to get a better idea what's maybe going on inside the solver. The plot on the top, you have the red, the naive, and on the bottom, you have the traditional. Let's try to parse it slowly here. The truth here that is unknown by the agent, that this is what the agent is trying to learn, is like the do x0, that is the solid line here, is greater than the do x1, that is the dashed line. Y given do x0 is greater than do x1. This is don't know. Now, in this data that is coming from the hospital, y given x1 is greater than x0. Then note here that as the prior that we have, by the way, I'm plotting here number of rounds, and the posterior here inside is 95 CI, confidence interval 95%. Note here that the lines are switched, flipped. The dashed here is the one that is the do x1 that is on top of the do x0. And based on what's going on here, it seems that there's a lot of weight and is not pulling anything else. Then it's kind of stuck there in some way. While the traditional one that is throwing away the data, it starts in 50-50. And then after, I don't know, a little bit less than 500, we are already able to, with high confidence, disentangle these two guys here. The do x0 is better than the do x1. Then after this time that we spend doing exploration, we already can just exploit, and everything is fine. For sure, the bar here, just note, this shade here, the uncertainty is much higher in the suboptimal arms as expected, as usual. Now,
so yeah, so he's showing some counterintuitive results. Again, I'm not really following how he set up the question. I'd love to see this on, I'll say it again, like, got this working on some Atari game. That would be really impressive, just to show why these ideas matter.
Man, this is bad, or I'd like to, in some way, in the question like, why is naive TS is doing so bad, I would like to try to understand this effect of the prior. And this is the effect, I forgot the number here, but I think it's like 1,000 or 5,000 samples that we have that we use as the prior. Here we have 250, 200, 100, and so on. We are going down. Note here that it's 250. It takes around maybe 2,000 rounds, interactions, until you kind of catch up with the blue one, that is the traditional, to be 50-50. For sure, you have less uncertainty here in this suboptimal here, the do x1, because we already put it a lot in the beginning. But still, in some sense, it's hard to compare. But in some sense, it took around 2,000 rounds to have this. And then you can have the kind of behavior that you keep going. This gets weaker and weaker. In 100, whatever. After 500, you're already able to distinguish in some way. And then whatever. Oops. And eventually, by the way, note here that if you keep doing that, this guy here is deteriorating to the blue one here that I make it shaded, but the one downstairs here. Which think with me, that's unbelievable, because our whole game is like, let me try to get 1 million data points from someone, and then I can leverage or kind of warm up my learning, and then I need to do less experimentation. That's the dream or the goal.
So that's the takeaway here. So however he set up this problem, he's showing that the less he's constructed a problem using causal semantics where less input data that you use to train the algorithm, the better the algorithm seems to do, and that's kind of flies in the face of all modern reinforcement learning. So I'd be curious to see what the solution is. But again, wouldn't you just love to see there's something in OpenAI, Jim?
Not what they're doing, the goal. Here, what we're saying is that is these very samples that are hurting. If you as eventually, yeah, I think it's clear in some way, which is, now I would like to explain a little bit more about this behavior and introduce or start talking about the issues of non-identifiability. This is just the causal graph that we had before. And this is the structural causal model that generated the previous plots. I'll not parse one by one. You can do it at home. Now, what we ended up doing, and we know that because we are the system designer, we are trying to understand the issue. Now, this leads, this guy here, this SCM, that is an observed nature, leads to these two different distributions here. There is the
all right, so he's deliberately constructed an example. So we got u is x is equal to u, and then p of u equals 0.3. So this is the ground truth model. So he knows what u is. And we're simulating from this model, and we're getting this data. And we got the intervention distribution of y given x, and the intervention, or y given intervention on x, and then y given x. And so we get a flip of sign here, or at least a flip of flip of sign in terms of x, the expectation of y given do x equals 1 minus the expectation of y given do x equals 0, expectation of y given x equals 1, expectation of y given x equals 0, and you subtract those two, you get a flip, you get a sign change. So it's kind of a Simpson's paradox kind of thing. But he's showing how bringing in past data kind of, where you don't account for that kind of confounding must be causing an issue. But it's important because it shows that more data is not helping.
L1 distribution, that's observation, and the L2 distribution, that is the experimental. This is just the behavior that what we had before, that is, we already can see that the do x0 is larger than the do x1. This is what we know after running, and this is what this implies, sorry. Then it seems to be a bad idea to do the do x0, and we can see also the flip here, that the cx1 is larger than the cx0. Those are the numbers that you have, 0, 3, 0, 1. In practice, we don't observe this guy. We are playing the game. We are playing the game exactly because we don't have it. If you have it, well, I'll go a few slides before, you say if the do x, maybe 20, do x is known, doing the optimization is trivial. I kind of argmax this guy or do some computation on top, some type of statistics or function of this distribution. The whole challenge is that we don't have this guy. And the obvious observation from the CHT is like this guy here, the y given x, or the layer 1 data, underdetermines layer 2 data. Then you don't know what's going on in layer 2 because there is more information in layer 2. Now, this guy was bad when you knew about the thing. But now that we don't, and all what we observed is 1, someone could say, x1 is looking quite good now, because 0.3 versus 0.1, shouldn't I just do it? Do x1, this is a joke here, causal joke here. Now you guys know as much causal as I do, then we are in the same team here of causal team. The joke, should I just do it? And you put the hand here. Now, this leads to important, this is a joke. This leads to important questions. How do I know? I know this pattern is not present in my data, that you have this type of behavior that I just showed. We don't know. That's the challenge. We never know. Does this then imply that I should throw away all the data not collected by me, the agent, and always learn from scratch? There's no hope in generality of running from offline, but for these two other modes that are very constrained, the answer is hopefully not, because the other conditions are very stringent. The agent and the kind of twinge agents, and much more than that, evolve in a similar way. Yeah, anyhow, let me... after all, is there any useful information in the observational data? And I'll say yes, there is useful information. And our goal is to try to understand how to leverage this L1 data or confounded data. We'll take a very simple approach, 3-step approach for the problem. Step one, we like to extract the causal information from the confounded observations. The solution that we take is doing bounding. You're not trying to do point identification that get the P of xy and pretend that P of y x that's computed from that, and pretend that this is the same. We're trying to bound the y given to x. Result, given observations coming from any distribution P of x and y, the average effect is bounded. There's this kind of lower and upper bound here that is given by these expressions. Important thing to note in the expression, that is, those are functions of the observation distribution. There's just things about, there's no do here, no layer 2 here. That's good.
So I've actually seen this be a major theme of Elias's work, is that, so in causal effects, like you just because you can't identify something doesn't mean you can't figure something out. And a lot of things that you can figure out are you have some kind of causal query and you can't figure it out from the data you have, but you can bound them. You can put, and hopefully, you might even be able to get a tight bound. And so, right, so like that's what we got here. Okay, lower and higher. So the lower is expectation of y given x times p of x. And then the upper bound is the lower bound time plus 1 minus p of x. And so And so if we're being kind of Bayesian, then the expected of y given do x is uniformly distributed across like that bound. I guess that's not particularly Bayesian, but if you're being probabilistic, yeah, like you can kind of think of it as somewhere in there, and so you can kind of just pick any. I mean, you might not be able to kind of find you still might be able to find an action that maximizes e of y given x if those bounds don't overlap. If they do overlap, then you kind of default towards the one that has assuming that you want that y is a reward, you kind of pick the bound that has the most probability of containing the reward, or pick the x that leads you to a bounded area of reward that's the largest, rather. Yeah, I mean, I've always kind of, whenever I read through these constraint mathematics and probability and causal probability theory, I always find it a bit tedious, but this is clearly a useful use case.
Now, different flavors that you can find about the bounding and others. This is the ones that I like, or whatever I think more, and it seems to be more related. Linear program format. Sorry, if you already have some result that is related to that, let me know. Linear program formulation, not the causal graphs. That is not the one that I gave. Or in other words, non-parametric. If you don't have any assumption about the F and the P of U, you can have this approach here through Balki and Pro or Zhang and Barenboim, playing with that in different types of graphs.
Sorry, what he's saying when he says, well, you don't have any assumption, what he means is, like, if you have some knowledge about kind of the functional form between the relationships of the ground truth model, then you can probably leverage that knowledge, but he's showing very general results for non-parametric SEMs where you don't really know what the SEM is.
Now, incorporation of parametric knowledge. If you know a little bit about the F in some testings, you could. There is this nice paper by Nathan that is also here in New York, doing Nathan Carlos and Zhu. If you know something about the SEM, about the functional form, or the U, you can get kind of tighter bounds. Then my suggestion in general.
I'm going to look that up. That looks, because I think we always know something about the bound. There's always something you can say about the system. You're never 100% naive. That's not going to happen either. I have no idea what this reference is if I can't find it. That's probably it. (2020). We propose the notion of a worst case. It sounds right. Across populations of given size, conservative notion of top line treatment effect. So this would be. So what is the treatment effect that the difference between do x, two values of x here, and the difference that gives you a causal effect or a treatment effect, or he's just calling. Yeah, so usually average causal effect means a difference between two things, but I mean, you have to calculate this to get a causal effect anyway, so I'm happy with that definition. But let's see here. Let's see, we got a worst case. What are the assumptions? Semi-parametrically. Propensity scores, Niemann orthogonality property, slower than parametric weights. So I can't tell what the assumptions are without reading it, I guess. What are the semi-parametric assumptions? Just must be this ortho. If we satisfy this orthogonality price. So that might be useful. Probably should look that up. Let's get back to it.
General is to start from these ones. If these ones work well, that's good. Or if you feel that they can work well, this is good. If they are very loose, then you can start seeing that what are the reasonable assumptions that you could use in order to speed up learning. And you have other settings, kind of more involved graphs that will come later. Second step, now we need to incorporate these causal bounds into the learning procedure. Here I'm picking the Thompson sampling because it's easy to explain. There's the UCB version that is easy to prove some results, and we can do in any other method or many other methods. I'm highlighting the changes here, causal bounds that you have for input for each layer, for each arm. And now you have some type of rejection sampling here to guarantee, to ascertain that the whatever you're sampling from the beta is within the bound.
Great, so let's walk through this. This is causal Thompson. So he's defined some bounds. And let's look here. So we're Thompson sampling is we're choosing actions based on the probability of being the optimal action. And the optimal action is, well, okay, so maybe this is a binary outcome. So we sample from this beta distribution. What is SX and FX? I don't know what those are. Are they, well, okay, they're parameter, oh, so they're parameters of the beta. So they must be some kind of count. So that's maybe where the past data comes in. And so we sample and then we sample a probability value, make sure it's in the bound. And then we do this thing where so I think theta here is the let's go back to the previous slide. So theta here must be this. And so we want to maximize that value conditional on x. And so for each x, we get a value there, and we just keep sampling until it's in the bound. And then we pick whichever, so we'll have, for each x, we'll have a theta value that we've accepted, and we shall pick the argmax. We'll pick x whichever, so basically the x of the largest theta. And so that's not actually, is that Thompson sampling? Because it was, it's causal sampling in the sense that you're picking so in a normal Thompson sampling, what do? I pick, so each x has a probability of being the best. So if we were being strictly technical here, we would, rather than using this argmax, we would sample x with probability given with weights corresponding to theta, but this is, so I guess this is what this sampling step here is where we start getting Thompson sampling-ish, but I guess I'm just being overly technical, but making sense to me.
The bounds, I'm assuming that you have tons of observational data. What about if you don't have so much data? You have some kind of finite samples of the observational. Now you can try to be more careful and put some kind of distribution there, a little bit less strict. There's a very good, cool problem. I think is a natural to consider this setting. But anyhow, here we have a rejection sampling kind of thing. Now the third question is like, what happens in practice? In practice, this works quite amazingly well. The whole game here, from the non-convergence that we have for using in a bad way the data, we go to, let's throw away the data, I cannot learn to anything. To a result that this is I can do with my closed eyes. It's very simple. We can the point here are kind of chopping. Now we are discussing about speed of convergence. We can kind of chop here a lot of this initial exploration. That is the whole goal of the observational data. Then in practice is a very easy instance. If 100, maybe 100 trials here, you already solve the problem. Now, third step in reality is like, can you, order of magnitude improvement can be achieved in practice. The step 3, I should write separately here. Can you prove that this translates to the regret bounds? You can check the reference, but that's the idea. Then first, let me summarize here. I think it's better. You have the causal graph here. You have many observations here. Recall that this is vertical lines, means data points. You have tons of them, 1 million data points. Now we'll apply this GPL bounding, and you like and we cannot get point estimate. Then you need to go online and need to do some kind of exploration. Now you have this policy pi that is influenced or is constructed based on this guy. And then you go online and do that. Then the step to do that template here of the task, if the policy is identifiable from offline methods, just return the optimal policy to the do calculus, the combination with IPW and other estimation methods. Otherwise, we.
So in other words, if offline, so he's given a nice little template here. So if you're offline and you have a whole bunch of data and you're trying to get the probability, you have X and Y, you're trying to get the probability of the probability distribution of Y given do X, because you're actually going to do interactions. If your causal, so identifiability means that the do calculus or inverse probability weighting or whatever causal inference technique you're doing will work given what you observed and what you're assuming about the environment, the DAG. Then if that works, then great. Just tell the policy to do whatever. Just, you have the probability of Y given do X, so all you need to do is pick a policy that does argmax E of Y given do X, argmax over X. But if you can't, then
extract the causal information from the observational data and compose the causal bounds based on the available structural assumptions. Can be assumptions on G or some of our work can be assumptions on the F of the P of U.
Then based on whatever assumptions you have, you try and construct these bounds, and then I guess from the offline data, seed that into your online algorithm in form of, I guess, in the case of that Bayesian, that Causal-Thompson sampling, the counts for the beta distribution, and then you do an explore exploit, and I guess if you wanted to be more exploratory, you could even, rather than doing that argmax thing he was doing, you can make it more. You can do proper Thompson sampling and sample based on those datas. Add a bit of noise, but anyway, I'm not gonna. But we have a nice workflow here. Start with offline, see if you have identifiability. If you don't, then construct those bounds and do a explore exploit kind of scenario.
You go Nathan and so on. And then you go online. You get offline plus online. You incorporate the causal bounds into the online allocation procedure and play. And the third step is theoretical. If you did it right, you can prove that these will reflect in the regret bounds. That's cool. I'm kind of running out of time here for this task, but I would just like to talk about quickly about one new result. There's this setting that is dynamic treatment regimes that is very popular in the medical domain by Susan Murphy and so that has cool result. That is, we have this nature that is x1, x2, and so on. And it's kind of more than MDP because we have this latent variable here affecting everyone, and it's also not exactly upon the P. It's more general in some sense, but I'll not get there. You can read more about DTR and these references and others. And the idea is like now we have the sequential aspect, and same thing, but now we have X, Y, and C, where C is the context, S1, S2, and so on. And now we can do GPL bounding there. And in reality, the results are pretty great. It's very, very technical, gets technical, the proofs, but the results are pretty great. This is randomized. This is by Murphy solution that is essentially doing the Fisherian randomization here, or a variation of Fisherian randomization here in this setting, the sequential version of this randomization. Here we have our setting here, our kind of solution, just exploiting the structural assumptions that is already in the DTR setting. And this is one, the green one is the one using observational data, which is a piece of cake. Essential observation data does the job. Just kind of a very cool result. This is the reason that I'm sharing here this paper I like to talk, or at least to call your attention or get your attention to check this out. Okay, I want to move to task 2. I'm slightly.
So that last little bit there was just saying, what happens if we're reasoning in. So he just basically gave a kind of bandit kind of scenario, right, where you're starting from scratch. He said, well, not from scratch, but like you're not looking at cumulative rewards. You're looking at instant rewards at every step. So that this what he's done here is provided a way of kind of looking at it over cumulative rewards. In this case, y is a cumulative reward, and x1 and x2 are ordered actions that all impact that cumulative reward. And then we also have some context variables here. So he's just making it more general. Although I would argue that if you really wanted to sell reinforcement learning people, this is the use case you would want to focus on.
Named by Susan Murphy and so that has cool result. That is, we have this nature that is x1, x2, and so on. And it's kind of more than MDP because we have this latent variable here affecting everyone, and it's also not exactly a MDP. It's more general in some sense, but I'll not get there. You can read more about DTR and these references and others. And the idea is like now we have this sequential aspect, and same thing, but now we have X, Y, and C, where C is the context, S1, S2, and so on. I want to move to task 2. I'm slightly slow here, but I think it's okay. The second task is when and where to intervene. Refining the policy space. This is work with Sangak Lee, my postdoc in my lab, the causal AI lab. Very nice work with him, and he will help.
All right, I want to stop it there and pick it up from here next time. But I'm actually enjoying this. He doesn't have that much to go. Too bad. Let's see how far we can. When and where to intervene. I want to get I'm hoping to get to the imitation learning. Counterfactual thinking starts here. We got, sorry. I'm going to call it now, and then we'll wrap this up next time. Thanks for tuning in.